Okay. Yes, correct. So, so we're gonna introduce Brendan Murphy, who's visiting us to talk about a model-based approach to enhance individual matchings across different databases using household information. And over to you, Brian. If you don't mind, I'm gonna move this thing out of the way.
Oh, yes.
Hide the floating control.
Great.
Excellent. All right.
Perfect.
Now over to you.
Great. Thank you very much for the invite to give the seminar. This is joint work that I did, or I'm doing with Pius, who's a PhD student that's being co-supervised by myself, and Michael Fott, who's a colleague of mine. And we're looking at the problem of record linkage, where we're linking different databases and trying to match individuals, and whether using household information is useful in this process or not. So I have two example data sets. The more interesting one is the one I actually do less work with, but I'll start with that one. I actually do have some results of that data towards the end of the talk. So basically, the Irish government have been digitizing old censuses. And in particular, they have the 1901 and the 1911 census online, and they've been digitized, and there's electronic versions of the records, and you can get the images of the census files as well. And when this data became available, we just had this question, basically, can we actually match individuals and households across the two censuses and see what actually changed in Ireland across that time period? And we also talked to some historians, in particular Paul Rouse, who's in UCD School of History, and he was very interested in the project, and he gave us some insight into this project as well. And a group in Carnegie Mellon University have actually done kind of different work on the same data. So Rebecca Nugent and her PhD student, Tyler Frizzley, they came to Dublin and actually working on different aspects of the problem, what I was saying today. And in particular, we think if you match the two censuses, you can learn a lot about what actually happened. An important thing just to mention as well is these two censuses were taken in 1901 and 1911. Ireland was still part of the United Kingdom at that time. So the census dates are the same as the UK, and pretty much the same structure as the UK census back then. Basically, it happens in very late March, early April, the census. It's usually, I think, Sunday at the interface of those 2 months. I know that's what it is nowadays. It's still more or less the same date, even to this day. So just to show you an example of a census form, and this census form, it might be a little bit difficult to read, but this is exactly the type of data that was digitized. So there were handwritten census forms. This is actually from my, so my great-grandfather would be the third entry, and my great-great-grandfather would be the head of the household in this data set. So this is what my family my father's family would have looked like in 1901. So there's like the head of the household, Dennis, his wife, Ellen, eldest son, Matthew, and then Jim. And there's even already weird things going on with this data, as mentioned. Matthew, for some reason, has been spelled with one T. And for some reason, there are two Marys who are the exact same age, and one of whom is married and one of whom isn't, which is a bit strange, and they're both daughters. So there's errors in the census forms from the start, basically. This is the same household in 1911. So actually, Dennis has passed away, and Matthew with one T is now matched with two T's. And he is married to a Mary, same name as his sister, different person, and actually they're children at this stage. So my grandfather is in there as the fourth row of 1911. Another weird thing that's happened, just to point out that linking individuals across historical censuses is very difficult, but this would be true in the UK as well. Matthew, even though the two censuses were taken exactly 10 years apart, has aged by 12 years. So if you look back, in 1901, he was 35, and in 1911, he's 47. Does anyone have any guess why that might have happened? Anyone in the room? It's quite difficult to hear online. they're taken, one is the 31st of March and one is the 4th of April, or the 3rd of April. There was a major law passed in the UK in 1908, which is basically the old age pension was introduced for the first time in 1908. Okay. Ireland was still part of the UK, and you'll see it throughout the census database. People start to exaggerate their age because they want to get the old age pension at some point in the future. You do sometimes get in historical data sets too that people round to multiples of 5 and 0. A concept that's called heaping. But in particular for this inter-census period, the old age pension was introduced on the 1st of August 1908, and that actually has a huge impact on the age variable for some people. So people mysteriously aged by a lot more than 10 years in some cases. In this case, it was only 12 years. So typical record linkage methods just trying to match individuals. And basically, we have a hypothesis that if you actually look at the household that the person comes from, it helps you match the individuals. You might get more accurate results. Now, we've some mixed success with this. I'll show you examples where the household information helps, and it seems to be quite useful. But I'm actually going to show a very statistical example that's probably going to be a counterpoint to everything I say that's coming later, which is actually to look at another person who happened to live in Ireland in 1901 and 1911. Where his household has changed a lot. So this is William C. Gossett, the inventor of the t-test. He had moved to Dublin just before the 1901 census to work in Guinness as a brewer. And he actually is living in a house where the head of household is on his case. These are all actually brewers. Guinness actually is interested a lot. They're all working as brewers, and they're all living in a house in Dublin city centre. Lots of young brewers. William C. Gossett is in there as the third person of the entry. His surname is misspelled because he didn't fill out the form. And basically he's 24 years old at that point. Yeah.
Can I ask you a favor? Can you stay near your laptop and
Okay.
maybe move the mouse?
Yeah, fair enough. Yeah, that's perfect.
Sorry.
Yeah, no, that's perfect. I'm happy to do that. 10 years later, in 1911, William Seeley Gossett is actually the head of a household. He is now living in Dublin, basically with his wife and children, and they have some staff in the house as well. And he actually has aged by the correct amount. He's aged by 10 years. Another weird thing with the census form, and I think this is probably true of all the UK census forms, in the 1911 census, they had a really crazy way of recording gender, that they had an age column or 2 age columns, and if you wrote your age in the left-hand column, you were male, and if you wrote your age in the right-hand column, you were female. And you can see that even William Seeley Gossett, who is a very smart person, made a few mistakes and had to fix them. Also, just matching individuals, one variable that we use a lot in matching individuals is a little bit unusual in the Irish context, is that even though Gossett himself has recorded his religion as Church of England, and his wife and his eldest child, his 2 youngest children, he's recorded at the religion as Church of Ireland, because they were probably baptized in Ireland. So the data are quite noisy and messy. So you would wonder whether household information would help with matching Gossett. That's just kind of a word of warning that some of the things I say, but I thought it's a nice statistical example to look at. Somebody we all have heard about, and somebody who would have had strong UCL connections as well back along. Another data set where I spend most of the talk just using, it's a standard data set in record linkage. It's basically the Bank of Italy conduct a survey every 2 years called the Survey of Household Income and Wealth. And it's a panel survey where some of the survey participants remain across the 2 waves of the consecutive waves of the survey. And the data is actually made available where you know which individuals appear in both waves of the survey. So this data is used a lot in record linkage as a test case for basically checking whether record linkage methods work, because we have a lot of individuals that we know they match, and we have a lot of individuals that we know they don't match. So we have a ground truth for this data, where in the Irish census data, we don't have a ground truth unless somebody has actually annotated the data, which I'll come to later. We have actually some annotated data that somebody has looked at. So basically, this is a nice data set for testing record linkage methods. We have a lot of variables recorded for the people in the Italian data. We have the individual's sex, whether they're Italian citizen or not, when they were born, educational qualification, the region they were born, where they work, region of residence, and employment status. We don't have any name information, so we won't have problems like Matthew becoming Matt and going from having 1 T to 2 Ts. We will have basically, we don't have that information, but we have all these features recorded on the individuals. And what we're going to want to do is develop record linkage methods to see whether we can link individuals with high accuracy. This just gives another example from this data why maybe using household information could be useful. Here we have a female who is an Italian citizen who's got a professional diploma, works in wholesale and retail in the particular region, and is a sole proprietor. And then we have 2 individuals that look very like that person in the second wave of the survey. But when we actually look at the other individuals in the house, it becomes much clearer that the first match would be the correct match. Okay, the second one, there is some differences like date of birth, but having the household information is definitely going to help us be more sure about finding the correct match for that person. So that's just showing an example of this. So the key thing we're going to do, we're going to try and develop an unsupervised record linkage method for matching individuals across different surveys. And we have the hypothesis that using household information will help. Now, we did actually develop a supervised method, which is quite different to what I presented, that we recently put up on archive and has been submitted to a journal. And we found in that work that household information helps. But quite often when we're doing record linkage, we don't have a ground truth. So we wanted to come up with methods where when we don't have a ground truth, we may be able to match individuals. So we're going to focus on the Italian data for the moment, but I will come back to the Irish data towards the end, which is work that's probably a day old, some of it. So it's work that HIAS is doing very much at the moment. So when I'm talking about the method, I want to just give some notation to start with. So for each pair of individuals, where the first individual comes from the first database and the second individual comes from the second database, we want to have an indicator, well, for households as well, we're going to have an indicator matrix that says, do the households match? So HST is going to be equal to 1 if household S in the first survey matches household T in the second survey. We're going to have a similar indicator matrix for individuals. So does person M in the first survey match person N in the second survey? We have capital S households in the first, capital T in the second, capital K is the number of variables we have. Kind of like you could saw the types of variables we have. And then the total number of individuals in the first and the second survey are M and N. They're less important. So one thing that's going to be very important is we're going to try and infer H and Z from, we'll have a model where we try to infer H and Z and match individuals using H and Z as a result. So we have this latent indicator variable that says which individuals match each other, and we have another one that says which houses match each other. Just to talk about the matching matrices for a second and why matching is going to be quite difficult, at least in principle, it could be quite difficult, and maybe it might motivate why we did what we did. If you think about our matrix of matching individuals, every individual in the first survey, the row of H tells who they're matched to. So, and likewise with households, if we take any household in the first survey and we go across a row of the H matrix, that's going to tell us which household they're matched to. So Z or H, they're going to have a structure. We're going to make the assumption that any individual has only one match in the second survey. So any row of the Z matrix has at most 1, 1 in each row, and it could have no ones. It could be that the person has no match in the second survey. Likewise, if you go down the columns, it's saying if you take an individual from the second survey and you go down the column, the 1 will tell us where which person in the first survey matches them. So the matrix the Z and the H matrix that we're interested in estimating that will allow us to match the correct matching of, or we're trying to estimate who matches who, which houses match each other and which individuals, is a binary matrix where each row has at most 1, 1, and at most 1, each column has at most 1, 1. Mathematicians have actually looked at these matrices quite a bit, less than I expected. It took a while to find some mathematical results, but the number of possible matchings grows really, really quick. So if we had a data, we could think of, say, if you had if you just had a 1 by 1 matrix, so if a house only had one person, if there's two possible matrices, it'll just either have the number 1 in it or the number 0 in it. So there's two possible matrices. But if you look at the number of possible matching matrices, so suppose you were trying to match two households of size 5, there's 1,546 possible matching matrices that would actually that could be the correct matching matrix for two households of size 5. If you have two households of size 9, you have over 17 million possible matchings. You need to see, we were trying to work out which one is our best estimate of correct matching. So it's combinatorially a bit of a nightmare. But we're going to assume that there is some latent Z and H matrix, and we're going to try and come up with an estimate of what the Z and H matrix is, and then use that to match individuals and households, and then see whether we actually did a good job matching the individuals and households. We're going to do this in a very model-based approach. We're going to take a very simple model-based approach. For the Italian data, we just have a binary matching matrix. Does the feature match across individuals or not? So for each feature, so for example, region of birth, citizen, occupation, all these sex, we're just going to construct a vector for each pair of individuals. We're going to construct a vector, a binary vector saying, do they match or not? Now, we're going to have a model that's got 3 components to it. Yeah. It's actually, we're told these people live in the same household in the data. It's given to us. So it is basically, yeah. Yeah, that won't be a problem. Yeah, absolutely. Yes, that can happen. Yeah, you can have that happen. Yeah. So basically, a household is, we've been told these are the same household across the 2 surveys. And these individuals within the household match. That's the nice thing about the Italian data. We have a ground truth to check our answers in the end. So we're going to say, basically, we're going to have for each feature, it's a very simple model we're going to propose, but we're going to have a theta is going to say, what's the probability that 2 individuals within a household, or sorry, 2 individuals that actually are the same person and are in a matching household, that they actually match on a feature. So we'd expect theta to be quite large. This is the same person 2 years away, 2 years apart. So we're going to have theta is going to say, what's the probability they match on citizenship? What's the probability they match in sex? We're going to have one for each of those. For individuals who are correct matches within matching households. Omega is going to be, what's the probability 2 individuals match on a feature, given that they are from the same household, but they're not the same individual. So that could be, you know, somebody's spouse being compared to themselves, for example. And delta is going to be, what's the probability 2 individuals match on a feature, given that they don't come from the same house. So the households are not. So you take 2 random people from non-matching households, what's the probability they're actually going to agree on a particular feature? We assume that the only individuals that match are within households that match. That's just a simplifying assumption. And that does restrict our approach a little bit, because if a household splits or merges, it messes things up. So we are assuming that the only matches we're going to find are within households that match, basically. We can't have splits and things like that. Then we just come up with a very basic, almost like a latent class analysis model, where we've got a much more complicated kind of latent variable structure, that the probability of what we observe, our data, for any pair of individuals given the value of Z and H, just has a conditional independent structure within each of these situations. So it's very like latent class analysis. So we basically work out what's the probability of the binary vector that says which features they match on and which ones they don't match on, given that the first term is given that they're the same individual within the same household. The second term is given that they're different individuals within the same household. And the last one is given that they're from different households. So that's that's our complete data. That's going to be the term that goes into our complete data likelihood. Our complete data likelihood is going to be what we get if we actually work this out for all pairs of individuals. So this is basically what's the probability of Z, H, and the parameters given X. That's our likelihood where we have the latent variables and the H. It's just going to be producting that over all pairs of households and individuals. And if we were to try and evaluate the likelihood function, it's actually computationally intractable because we actually have to do a massive summation over all possible matchings of households and all possible matchings of individuals within households. So the likelihood function is actually not really computationally tractable because you're summing over all possible Z and H matrices, and we already saw that they're vast in their number. So we're not actually going to be able to work with the likelihood very easily. Now we're going to take a very straightforward approach, possibly too straightforward to actually fit the model, where we're going to take our complete data likelihood and we're actually going to maximize with respect to the parameters and the two latent variables. So normally we try to do some sort of EM algorithm, or we might try to do some Bayesian inference, but we're actually going to try to maximize the complete data log likelihood where the Z. So we're going to maximize with respect to H, with respect to Z, and the parameters, and see what we get. Now this is what's called a classification EM algorithm in the mixture modeling world, where you, instead of trying to maximize the likelihood, you try to maximize the complete data likelihood. And it's got two steps. The first step is called the classification step, or the C step, which basically is we're going to maximize the complete data log likelihood with respect to H and Z. So we're going to try and say, keeping the parameters where they currently are and the data that we have, what would be the H and the Z that maximizes the complete data log likelihood? Then we're going to fix H and Z, and we're going to maximize with respect to the parameters, and we're going to iterate. So this is what's called a classification EM algorithm, where it replaces the normal E step with an optimization instead of computing an expectation. And these steps are repeated until convergence. Now, we did this for pragmatic reasons because we can actually get answers, and we haven't worked out how to get an EM algorithm, or maybe a Monte Carlo EM algorithm, or a Bayesian. The complete data log likelihood, just this is written out exactly in the form, putting together the model we had previously and the equation for the complete data likelihood is of this form. It's worth noting when you look at this expression, it's actually a linear function of the Z entries, and it's a linear function of the H entries. And we know a lot about the Z and the H matrices. We know that the Z matrices, the rows and the columns are less than or equal to 1, basically. They have to be less than or equal to 1. So we can actually optimize with respect to Z and H. If we fix Z and optimize with respect to H, or if we fix H and optimize with respect to Z, we actually have a straightforward optimization problem that can be solved using linear programming. And then if we know Z and H, optimizing with respect to the unknown theta, omega, and delta parameters is actually straightforward. It's actually they've closed form expressions. And that's what we do. Yeah. It ends up being that they're binary, yes. It's a linear program and the solutions end up being binary, basically, yeah. So it's kind of an assignment type problem, if you want to think of it that way, which is a special type linear program. So as I said, when we're optimizing with respect to the H matrix, it's a linear function of H. And we know that the H rows and columns add up to numbers less than or equal to 1, and they're binary. And when we solve that, it's just a linear programming problem, and we can find solutions very straightforwardly using linear programming. So that will give us an update to our H matrix. If we fix H and we optimize with respect to Z, we also get a linear program, and we can solve it very straightforwardly using just standard linear programming methods. And then once we've Z and H updated, we can update the parameters. And these actually are just closed form estimates. You do have to do summing over lots of entries. You can do them quite quickly. They're just counting things actually. If you actually look at the update for theta, it's actually just saying what proportion of times did matching individuals within matching households match on that feature. Yes, is there a question?
So you two-step H Z optimization, is that guaranteed to get you the bivariate?
We iterate them, so we do kind of this update H, Z, H, Z. Yeah. It could get stuck. It seems to be, doesn't seem to get trapped, but I imagine we have no guarantee that it's going to get us to a global update. Yeah. Yeah. But it seems to be working very well. Yeah. But it's kind of like a coordinate ascent thing, and it does seem to be getting us up to, but the structure of the problem seems to be okay. Same with the omegas. The omega entries are for non-matching individuals within matching households. What proportion of times did they match in that feature? And likewise for the deltas, for non-matching individuals within non-matching households, what's the proportion of times they match on a particular feature? So the updates are actually very straightforward and intuitive for the parameters. Just something that people may or may not have heard about before, for the Italian data, it's still quite computationally intensive to actually do the matching. We can actually get it to work on the entire data set, but it takes a while. And I should actually know the amount of time, but I've actually forgotten. I did ask Thijs a few weeks ago and I've forgotten. But basically, it does work. We can actually run our algorithm on the entire Italian data. And likewise, when I get to the small subset of the Irish data set we're using, it works in close form as well. We can do it in a feasible amount of time. In record linkage, it's a concept that's used a lot. We have the concept of blocking. So blocking is the idea that you divide your data into non-overlapping subsets, and you only do record linkage within those subsets. It's just a concept that's used a lot in record linkage to get around this concept if you can't do it. We looked at basically blocking on region of residence. So in the Italian data, we decided when we're trying to do matches, what we're going to do is we're only going to do matches within region of residence. So if somebody moves from one region of Italy to another region of Italy, we won't be able to match them. Turns out that well, in Ireland, people aren't very mobile within the country. They were probably more back then, but in Italy, Italian people are very loyal to where they kind of live. They don't move very much. So I was reading the literature from kind of the sociology, demography, geography kind of literature, and there's one reference here. You will get kind of at most 1% of people move in a year, basically, in Italy from one region to another. It's very low rate, basically, and it's actually lower now than it would have been historically. I think up to the 50s and 60s, there was a lot of mobility in Italy, and it's very, very low now. And actually, people are they stay living in the region that they have been living in. And when we're doing the Italian matching, we must remember the two surveys are only 2 years apart. So the chances of moving region is actually very low, given the Italian context. I didn't know about the scientific literature, but Michael Fopp, the other co-author, is Italian, and he said, no, we don't move region in Italy. It's very rare. So that's why we originally did it, but it's supported by the science. Yeah. That would be a very good idea. Now, for the Italian data, the blocking has very little impact on the results, but it would be a very good idea in other contexts, I think. And I actually think when you actually try to match, say, if you're trying to match the two entire Irish censuses, no one method would get you everything. So you should almost do blocking, get what you can, see what's left over. You know, I think to actually do a full matching of some complicated data set like a census, you'd have to take a load of approaches. So what I'm proposing here would get us some way, and to catch people like Gossett, we'd need another approach, and so we worried a lot about initialization methods. As kind of some sort of oracle, we actually started with the true value of Z and H just to see how we do. We used a very standard matching algorithm called the Figeli-Sunter model to initialize, which is basically a way of matching individuals that completely ignores household information to get an initial value for Z. We took that as one option. And then if we have a lot of individuals together that match, we kind of said, well, that's an initial household match. So we used it to get kind of an initial household match. The Figeli-Sunter model is very much like our model, but it ignores the household information. It basically is like a latent class analysis model with two groups, the matching individuals and the non-matching individuals, and it just basically estimates the parameters, and it's usually fitted using an EM type algorithm. And then we also just looked at randomly initializing H and Z with some valid values of H and Z. We compare all of our methods at the end, well, when we're matching individuals, to the FastLink package, which is basically a way of matching individuals using Figeli-Sunter, which is kind of a very standard OR package for record linkage. When we're matching households, we can see that we can actually do quite well. We have quite like I'm just summarizing our results using kind of the F1 score, the precision, and the recall. We get an F1 score of 62%, which is actually very close to if we actually initialize with the truth and run our algorithm from there. So Figeli-Sunter actually is quite good for finding starting values for our algorithm. If we randomly initialize, we do a bit worse. This is done with blocking. If we don't block at all, these are the performances we get from matching households. So the column with all data is where we don't actually do any block. And the results are kind of comparable. So we're actually doing pretty well matching individuals. Very high precision, or very high recall, the precision is a bit lower, and overall the F1 score is in the 60s. When we then go to matching individuals, we're doing very well with our method. So it seems like a good approach for matching individuals is to use our method and initialize using this Figeli-Sunter model, which is very standard for matching individuals. If you ignore the household information, I've got two FastLink results here. One of these took a long time to get. It's running FastLink where we do blocking versus FastLink when we don't do blocking. They've got much worse performance statistics than basically if you ignore it. So using the household information does seem to be enhancing the results. You know, you could argue the results are not amazing, but they're a lot better than what the standard methods are doing. So we're definitely getting a lot of cases that standard methods are missing. And I think there will still need to be more methods to get even more matches. The parameters make a lot of sense. So I'm showing you kind of dot plots of the parameter estimates we get. For each dot plot has got 4 sets of values, which are the different initialization strategies, and then the parameter we got within each block. So we did blocking. So within each region, what was the parameter estimate we get? So for example, the parameter, the theta value, the second column is probably the most interesting one because that's what we're kind of advocating as an approach. If theta for sex, so if 2 individuals are within the same household and they're the same individual, they're almost certainly going to match for sex, which is not surprising. If you take 2 random individuals within a household and the household matches, the probability they match on sex is actually just under 0.5. It's around 0.5, but it seems to be a little bit below 0.5. And then if you take 2 random individuals in the population that don't match, the probability they match on sex is about 0.5 as well. If you look at, say, qualification, I'll just talk about this one. Again, the theta is high. The omegas, which is basically individuals from the same household who are not the same individual, they're lower. And then for non-matching individuals, they're lower again. So you do kind of get that pattern. Typically, theta is bigger than omega, is bigger than delta, except for some variables. You will find sometimes that the second one, the omega, is slightly lower than the delta. So for example, the sex one, we find that consistently that 2 individuals within a household that are not matching individuals, they're slightly less likely to match on sex than if you take 2 random people from the population. That's just something that seems to come out a lot in terms of the study. And here are, these are just the ranges we got across the different blocks. And you can kind of see the general pattern that theta tends to be bigger than omega, tends to be bigger than delta, except for the sex variable. It's kind of, omega's a little bit lower, it seems to be. So moving back to the Irish census data. So that's our method applied to the Italian data, where we took our features to be whether the individuals match or not on a particular feature. That's how we compared individuals. So we binary data for each pair of individuals and a binary vector depending on the number of fields that are in the database. Now this is very much preliminary results that I'm going to finish the seminar with, which is basically going back to the Irish census data, but actually maybe trying to look at how different people are in a more nuanced way than just are they the same or are they different. So purely by chance, I've actually no idea why he contacted one of my colleagues, contacted one of my actuarial colleagues, a retired actuary called Dermot Balson, contacted one of my colleagues who's a lecturer in actuarial science and said, I have looked at the part of Northern Ireland where I grew up as a child, and I've gone through all of the census records from 1901 and 1911, and I've tidied them up. I've basically corrected name spellings as best I can. Religion is a really messy variable. Like, say, Church of Ireland, people will have Church of Ireland, they'll have Protestant, they'll write COI. They're free text, so they'll write loads of things. He's made them much more consistent than they are in the original data. And he also basically worked out which individuals match across the entire region, basically from both censuses. So he gave us a very well curated and annotated version of the Irish census data from this part of Northern Ireland, kind of near the Mourne Mountains, which is kind of south of Belfast, just to kind of show you. So this region of Northern Ireland. And he said, does anyone in your school have any interest in this data? And Adrian O'Hagan, my colleague, was like, well, Pius is doing her PhD on record linkage. This is exactly the type of data she wants, where basically, you know, you've given her a really nice data set to potentially look at. We have some annotated data from a few other regions that we did ourselves, much smaller regions. And I'll come back to that a bit more later, because the approach we're taking seems to work very well in some regions of the country and not so well in other parts. So in this data, you saw the original census forms. We have people's name, their forename, their surname, their age, their religion, their occupation, relationship to the head of the household, sex, whether they can read or write, etc. So we have a whole load of features. Some of them are categorical, some of them are text, and some of them are numerical. So we looked at a lot of different approaches, but for measuring the difference between two text strings, we used what's called the Jarrow-Winkler text distance, and it's an edit type distance. It says, I have two words, how many edits do I need to make to turn one word into another? So that can be quite useful when you're looking at the Matthew with 1T and 2T situation. Jarrow-Winkler will actually kind of capture that quite well. We did look at other distances. There's a really interesting distance called soundex, which actually, given how a word is spelt, it actually estimates what they would sound like, and it compares them in terms of the soundings of the words. Doesn't work very well with some Irish names, because things like BH are pronounced like V, and that wouldn't be obvious from the soundex. It works quite well for the English language. Somebody, I think, has tried to develop a soundex for other languages. We looked at lots of different distances like that. We tended, for the categorical features, just do they match or not, which is like the Hamming distance. And for age, we just took the difference in age. And we actually just modeled, we didn't even take it as a distance. We have a feature, which is what is the difference in age between the individuals. Just to show you a histogram of some of the kind of features and the distances, this is basically, there are three columns here. We have matching individuals within matching households are in green, non-matching individuals within matching households are in kind of light blue, and then non-matching individuals within non-matching households are in kind of the kind of pink type color. So we find basically, as we'd expect, the green bar is very close to zero. If people are actually matching each other, they tend to have the same surname, and the data has been very cleaned up. Individuals within a household have a very strong tendency to match in surname, but some people don't. There is some people have surnames that are a bit different. And then if you take two random individuals from the population, the surname is actually quite unlikely to match. The distance between the surnames gets quite big. So the distance has been scaled, so it takes values between 0 and 1. The maximum it can take is 1. Forename, you get similar structure, except forename individuals that match are very similar, but then the non-matching individuals, there isn't that much difference between if they're from the same household or not. Occupation is a mess in the census. I had a whole master's student work with the equivalent of the National Office of Statistics in Ireland, Central Statistics Office, just trying to tidy up occupation in the 1911 census. He managed to do quite a bit of work using just very basic kind of machine learning methods to tidy up occupation, and maybe kind of, because it was a free text box. So you'll have secondary school teacher, primary school teacher, teacher in St. Joseph's School. It's just a mess. You know, you'll have age. The matching individuals do tend to have age differences quite close to 0, but it's very peaked, but there is kind of a little bit to the right. You're getting some age differences that are actually quite positive, as I've already mentioned. For the PhD student, for some reason, took the difference in ages divided by 10. So a difference of 0.1 on that plot is actually a year, basically. But it's just a scaling, just to kind of keep things similar. And then for non-matching individuals, the age differences can vary a lot. So it's very difficult to find, this is where we are at the moment. We're finding it very hard to come up with a distribution for the distance between individuals on a particular feature, depending on which category of the 3 categories they fall into. So at the moment, what we're doing, and it's working quite well, is we're binning the distances into 5 bins. So kind of small, like 5 categorical bins. And we've looked at different ways of binning. If we do this, we get quite good results. We're getting not as good maybe as the Italian data, but we are actually able to get some decent matching of households, and we are able to get decent matching of individuals across households. And we're doing a lot better than FastLink, which is a method which ignores the household information. So in summary, we have found that basically using the household information definitely gives us some help in matching individuals. We're doing much better than the methods that match individuals without using the household information. We still have a long way to go. We're still working on kind of methods to deal with data like the Irish census data. It does really badly in urban areas because I think our assumptions that households might move, but they don't split and merge, actually doesn't seem to work quite well. You have a lot of people moving from one household, to another in urban areas. Street names, actually, it was a period coming up to independence in Ireland, and street names were changing. There was a lot of kind of streets named after places in the UK or famous UK people who were being replaced by kind of more Irish street names. So it gets much, much more difficult in urban areas. The methods I've described actually work quite well in rural areas for matching individuals within the area, people who are still living in the area. But we would like to look at modeling households, maybe people moving between households and households splitting and merging. That can happen. You can see that in the data in some places. Like in the UK, there is a law that says they can't release a census until it's 100 years old. Ireland didn't actually have a census in 1921 because there was a lot of political turmoil in Ireland. The UK census in 1921 was even delayed. I think it was kind of in July instead of April because there was a lot of problems in the UK. I think kind of protests and stuff, just labour problems. So the 1926 census is coming, so that's something we will actually be interested in looking in because it's such a huge period of change in Ireland. The algorithm we're using for fitting the model is probably the most basic we can do, where we're trying to optimize with respect to everything, the Z, the H, and the parameters. I'd be much happier with some sort of EM algorithm where we're actually averaging out the H's and the Z's, or doing everything fully Bayes going forward. So we can actually capture the uncertainty in the matches a lot better. At the moment, we're really just saying this is the best match. And we've no concept of the uncertainty in the matching process. It's not that easy to potentially do some of the sampling to do, say, a fully Bayesian Monte Carlo approach for this. Coming back to the structure of the Z and the H matrices, there is some quite recent literature in the probability community of how to sample matrices like our Z and H matrices, a uniform distribution on those. So maybe we can adapt those to actually try and sample from the posterior distribution you would have for Z and H. But at the moment, people are even working on methods quite recently to get good Markov chain Monte Carlo methods for sampling just from the uniform distribution on those spaces. It's not trivial even in that case. So that's kind of where we're going in the future with this work, and I'm happy to answer any questions on that. Yeah, thank you.
Questions from the room or from online?
Open the chat as well.
I want to know whether you could make these slides available.
Yeah, absolutely, 100%. Yeah, yeah. Yeah.
It's about 100% matching is probably unrealistic.
Yes.
You try to basically get to a point where the remaining, the person can check your matches.
Yeah. Yeah.
How good is, anything about how good how far away they are thing?
Well, they're not. Talking to historians, they actually would be really happy. They would love as an output, and it might be something that gets built in stages, that you give them a matching, and for each matching, you have a data set saying, I think this individual in 1901 is this individual in 1911, and this is the probability that we think they're a match, and likewise for the households. And it's up to the historian how they, like, am I happy with a 77% probability match, or would I still be happy with a 40% probability match? But they have some measure of certainty. Some of them are really obvious. It's like you always go, these two people must be the same individual. So I think the other thing I think that really surprised me, and it probably means that maybe the 1926 data, trying to match that back to 1911 won't be that useful. The life expectancy in Ireland in 1901, 1911 was 50. Like, it's amazing it was that low. So a lot of people, won't have a match, like if somebody's 50 in 1901, there's very low probability they're going to be even in 1911 census. So you're right, we're not going to be able to match everyone. And just some people are so difficult to match. Like, I know, looking at my own other parts of my family, I showed you the really easy case, but like one of my great grandfathers, he moved entirely across the country, for example. In my wife's family, one of her great grandfathers is there in one of them, but he was actually a prison officer in the second one, and they have a completely different kind of, and even army people, like some of the old census, they get really interesting, the census forms for the army, the prisons, and the psychiatric hospitals actually they're very, very unusual what they recorded for some of those. So I think just to get some matching and to see what actually changed, the historians think would be very good. But their ideal output would be we think these individuals match, and this is our kind of confidence in how well we've matched them. I think that's the best we can do. And hopefully we'll have more and more matches than non-matches as time goes on, and a level of confidence in that. At the moment, no. So that's why we want to go down more the EM type approach. Yeah.
Okay, question maybe about, how you were saying you wanted like to clean the work line.
Yeah.
But I not necessarily think is that it's wrong, right? People probably change between being headmasters and being.
Oh, yeah,
teachers.
absolutely.
So maybe that's not quite a good argument for one to on because that's a more,
Well,
a less permanent thing, right?
well, there is actually an extra piece of information that happened in 1901 and 1911, which was when the data landed into the equivalent of the National Statistics Office, people did manually put people into bins. So we actually, it's some information we haven't used in this project, but I did with the master's student. We actually have an estimate of, say, how many people were teachers, how many people worked in agriculture, how many people worked in, manufacturing, So what we actually worked on for that master's project was we tried to take the free text and predict which,
Right frequencies.
to try and get close to the right frequencies in the end. So rather than taking what the free text form was, it might be better to actually replace occupation with your best guess as to what bin they would have put in. But we don't have the information what the people did back in 1901 and 1911. We just have the overall, like for each county, how many people fell into each kind of category. But you're right. It's a really interesting one in the Irish data is relationship to the head of the household. That feature has no use in matching individuals, mainly because of when you go back to the two forms from my family, the son of the head of the household was the head of the household in the second one. If his sisters were still living with them, they'd have gone from being daughters of the old head of the household to being sisters of, so that one is actually just 0.5, the probability two individuals matched nearly in every case, basically. So that's a feature that has very little information. I think the occupation, if it was cleaned up, might. Also, the religion one is an interesting one. It was an interesting period in Ireland. You can see people in 1901 put down their religion as Church of England, and in 1911 put it down as Church of Ireland. Like the country was heading towards independence. Like it was kind of, people felt it was coming, and the people were getting more nationalistic. There are questions I would like to answer as well at some stage, talking to the historian Paul Rouse, for example. I think some things like, say, religion and the whole age thing, I think there was probably a correlation, certain or geographical. Some people in rural areas might be more likely to fake their age than cities or misreport their age, That's another thing. I've in my lifetime as a lecturer, I have met PhD students who don't actually know their age. They made up their age when they got their passport to come to do a PhD. Their family basically, and I actually have friends who are literally the same age as me that discovered when they went to get their passport that they'd been celebrating their birthday on the wrong day all their lives until they actually saw their birth cert and were like, Mum, you told me I was born on this day. I was actually born on this day. So people actually don't know their age sometimes. Yeah, you're all right. And there's that heaping effect. That's well known in social sciences, that people round multiples of 5 and 10. The questions on.
So David.
Oh, somebody asked me to go back to the second slide. I can see on the chat there. What was my second slide? This one? This is the second slide, or do you mean the? Yeah. But I can make the slides available. I can send them to Nathan. Yeah, I'm happy to make them available.
So
Yeah.
if we don't see any questions in the next few seconds or so, we'll consider this finished. Thank you.
Great, thank you. Like this.